And I am sharing the program schedule of today. So as you can see, at 10:15 a.m., Professor JP Singh is going to address the conference. So I would like to request Professor JP Singh, the convener of the conference, the International Conference on Sculptured Thin Films, GLAD 2021. I would like to request Professor Singh to welcome the participants. So over to Professor JP Singh.
Yeah, so dear all the distinguished speakers and participants, I wish good health for you and your family in this difficult time. And I express a warm welcome to all of you to this second international conference on sculptured thin films, GLAD 2021. So this conference aims to discuss the recent advancement in the area of nanostructured thin films grown by physical vapor deposition techniques. The first edition of this conference, GLAD 2018, was organized in March 2018 in New Delhi. But due to the present situation, it was planned virtually. And we hope that this conference will bring out cutting-edge development in the domain of nanofabrication techniques, especially oblique and glancing angle deposition. We encourage the scientists, faculty members, research associates, postdoctoral fellows, and PhD students from all over the world to participate in this online webinar. In this conference, we have 18 invited lectures by the renowned distinguished professor in this area. We have also 4 oral presentations by researchers working in oblique angle or GLAD technique. I encourage all the participants to take part proactively and discuss their queries with our speakers only after the talk. I hope you all have read the guidelines for joining the meeting sent to you over email. If you have missed it, please check it on the conference website glad2021.iitd.ac.in. Please listen to the speakers carefully and make sure that you have turned off your audio and camera to avoid any noise in between the talk. So I once again welcome all of you to this GLAD 2021 and hope you will enjoy all the sessions of the 2-day webinar. Now I would like to request Professor Yiping Zhao from University of Georgia, who is also co-convener and a kind of a founding as well as pioneer researcher in the area of glancing angle deposition, to inaugurate the session and welcome, give his kind of address note to the participants as well as the speaker. Over to Professor Yiping Zhao.
Hi, Professor Yiping Zhao, your voice is not coming. So can you unmute yourself?
Now?
Yes, now it is okay. Yes.
Yes, good morning. Welcome to the conference. So I just wanted to give a very short brief note about the current development of glancing angle deposition. As many people already know that in this conference, the glancing angle deposition essentially is based on the so-called self-shadowing effect during the deposition if people actually can manipulate the shadowing during the deposition. However, in a broad sense, if people actually can manipulate not only the self-shadowing, but can also using different kind of mask or template, you can also dynamically change the shadowing effect, right? So that is a very broadly defined glance angle deposition technique in my sense. So if we actually look at the literature, actually this morning I did a very simple literature search. If we only look at the oblique angle deposition or glance angle deposition, or the so-called dynamic shadowing growth or sculpture thin films, the total number of publications so far is more than 4,000, and the citation actually increased almost linearly every year. However, if we expand that scope a little bit, so if I include a well-known technique called a nanosphere lithography, which people also using a lot of shadowing growth techniques and also shadowing lithography, then you can see that the number of publications almost doubled, and also the total citation is huge. It's much larger than the only defined glance angle deposition. And also, there's also other ones like, for example, shadowing mask, how the people use, also edge lithography, and if people including that, so there's also more than almost like 10,000 papers so far, almost 10,000 papers. So that means if we can broadly define glance angle deposition, essentially is how to using the shadowing effect to achieve desired nanostructure and also devices. So this field, if we look at them, is still very promising, and there are still a lot of works need to be done, for example, to study the growth mechanism, to actually design new structures, and also to use them for new applications. So I hope that everybody can enjoy this meeting and also learn from each other and also push the field forward. Thank you very much.
Thank you, Professor Yiping Zhao, for the welcome address. So our first speaker is Professor Pierre Fischer. So I think he has joined the meeting. And I would like to request Professor JP Singh to introduce Professor Pierre Fischer. Yes, he is already here. Professor Pierre Fischer is here. So
Yeah, means like hi, Professor Fischer. Yeah, so Professor, let me just see. Yeah, Professor Pierre Fischer is a professor of physical chemistry at University of Stuttgart, and he heads the independent micro, nano, and molecular system lab at Max Planck Institute for Intelligent System in Stuttgart. He received his BSc degree in physics from Imperial College London and PhD from University of Cambridge. He was a NATO postdoctoral fellow at Cornell University before joining the Roland Institute at Harvard. In 2009, he received an Attract Award from Fraunhofer Society, which led him to set up a photonics lab at Fraunhofer Institute for Physical Measurement Techniques in Freiburg. In 2011, he moved his lab to Max Planck Institute for Intelligent Systems in Stuttgart, and since 2013, he is a professor at University of Stuttgart. Pierre Fischer is a founding editorial member of the journal AAAS Science Robotics and a fellow of Royal Society of Chemistry. Pierre Fischer is one of the pioneer researchers in the area of active nanostructures. So I invite Professor Pierre Fischer to deliver his talk. Over to Professor Pierre Fischer.
Yes, thank you very much, JP. Thank you for the introductory words, and thank you for putting this meeting together. I am honored to be allowed to open this meeting on shadow growth and glancing angle deposition. And as was mentioned, we're based in Stuttgart at the university and at the Max Planck Institute. And I'll talk about active nanostructures and the growth of these structures using the shadow techniques that were introduced by Yiping Zhao and JP Singh. So thanks to both of them and their helpers for organizing the meeting. And before I start, I think it's nice to show a picture of the meeting of 2018, which was held in New Delhi and organized by JP Singh. And here's a picture of many of the attendees. This is Dhruv Singh giving a talk. And it was a special meeting for me as well, because not only did I attend in person, but actually I very rarely, because it was such a special conference and location, took my family with me. And of course, these were happier times then. And it was very special. In fact, my children now think that every time I go to a scientific meeting, it's in a wonderful location with excellent food and wonderful hospitality. So when I tell them that this was the exception rather than the rule, the 2018 GLAD meeting, they don't believe me. But it was a wonderful meeting. And of course, now this isn't allowed. And now there's a sort of critical situation all over the world, and in particular in India. And so my best wishes to everyone. Stay healthy, and hopefully very soon we're back to normal, that we can meet like this. So thanks to the organizers for still going ahead with the meeting in these difficult times. And I think it's good that we can continue to discuss and exchange ideas. And with this, I would now like to start the more scientific part of my talk. And before I start, of course, I am very grateful, and I want to thank my group members. This was still when we were not wearing masks. And in particular, today I'm going to talk about some projects where I want to thank Thanasi, Dr. Athanasiadis, Jan-Philipp Günther, Ting-Ting Yu, Johannes Sachs, and Michael Popescu. And of course, various funding sources and helpers in the lab. And before I start, since it's a small community, I want to introduce the people who do the research, especially on vapor deposition and glancing angle deposition. And so our lab is run by two very experienced senior postdocs, Dr. Hyuna Kwon and Dr. Hannah Noah Bharat, helped by Connie Miksch. And we have two student projects, Vincent Kadiri and Ting-Ting Yu, who have used it a lot. And here you see our experts in front of a chamber, and many of you probably have similar chambers like this. So there is some kind of source down here for heating, either be it E-beam or thermal. Then there's a large distance to the substrate to make sure one has directional deposition. And as you can see, we can see the wafer face here, which means we can see that this is an oblique technique. And then there are controllers to manipulate the substrate during growth, and sorts of microbalances to measure what's going on. And with this, I'd like to talk about some projects that were done last year, and each of which was really motivated by a science question. And it turns out,
Please share your PPT, Professor Pierre Fischer.
Okay, you could have interrupted me a little earlier. I thought it was fine. I thought I had shared it. Is it shared now?
Yes.
Okay. Well, we're still in good time and it's very early here, so that's probably was my mistake. Since we're in time, I'll just show these pictures again. This was the meeting in 2018. Here are the attendees, and my children visiting and Ruth Singh giving the talk. And this is the thanks to my research group, the people whose work I'm going to present. And here is the GLAD team that runs the research and operates our instruments, Dr. Hyuna Kwon and Dr. Hannah Noah Bharat. And here, this was the picture that I was showing, which is the sort of setup that many of you are using. Again, here is the source, large distance to the substrate. Here is the wafer, and there's a manipulator here that allows us to manipulate the substrate during deposition, so we can turn the angle and we can ensure that there's shadowed growth. Now, this is the outline for today's talk. I'd like to discuss these projects here, each of which is motivated by a science question, and it turns out that shadow growth and glancing angle deposition both are useful in addressing these and solving these issues. And so let me begin with the first one, which is on micro swimmers, and we want to make a pump. And again, it turns out that shadow growth can do it. Then I would like to talk about single nanoparticle spectroscopy. And this is again a problem that was possible here with a GLAD deposition. And finally, the last one is again a GLAD deposition. So let me start with the first topic. And you're all familiar with microfluidics. Microfluidics are typically very nice systems for controlling fluids at small length scales. And what we also need to do is we need to pump the fluid. And so you can see a lot of pipes and connections, and these are auxiliary equipment, pumps that drive the fluid through the microfluidic chip. Now, this typically makes this much more complicated and less compact. And so the first research question is, can we make a microfluidic device, realize a microfluidic device where we have self-pumping channels, i.e. channels where the fluid, okay, I don't know what this is. We have a fluid system here where we are not talking about capillary flow, but where we want to have pumping, but pumping along the channel without external connectors. Is this possible? Now, the story starts with colloids, and it starts with Brownian colloids. So these are silicon dioxide colloids in solution that undergo Brownian motion. And they are the typical normal passive Brownian motion colloids that jiggle about because of thermal fluctuations. And we want to make a pump, but I'm going to tell you something else first. We want to first turn this colloid, which just passively moves in solution, into one that can actively move in solution. And in order to do that, we need to modify it. And one way to modify it is to include a reactive patch. So there is a region here that can cause a reaction. And if there are few molecules in solution, molecules that can react with the surface, there can be reaction products. And these reaction products will then arise at the side of the colloid where the catalyst, for instance, is that causes the reaction. And now we have taken a simple colloid and we've turned it into one where we have changed the environment. So the left side is different from the right side. And this means that there will be flows. So there will be fluid flow because we want to, or typically nature wants to even out these inhomogeneities. This is not an equilibrium system. It's now a non-equilibrium system. There's a reaction taking place. There is a flow. It's very hard ab initio to predict which way the flow is. And so there is a flow here to even out this concentration difference. And since the fluid is incompressible, if there's a flow from right to left, the colloid needs to go to the right. And this is what is known as self-phoretic, because the colloid itself causes the phoresis or the motion. Here is a system that John Gibbs made. He'll be talking later in the meeting. This is with platinum in a hydrogen peroxide solution. There are two linked together by a bar, and they keep rotating. And they keep as long in motion as long as there's fuel. Now, the curious thing in this whole thing is that if we take this colloid here and it, for instance, moves from right to left, it isn't because there's a pressure on this system. There is not a pressure directly acting on it. It's because there are tangential flows on the surface, which is the interesting phenomenon here. So let's say you have these purple reaction products, these purple product molecules. They will have an interaction with the surface. It can be an attractive one. It can be one that is maybe repulsive, but because there are more reaction products here than there is a difference in concentration. Therefore, there's a difference in the interaction. And that means if there are interactions with the surface, there is a tangential pressure difference, which causes the tangential flow. And because there is a tangential flow, the fluid moves along the surface of this activated colloid. And we are going to use a more sophisticated system. We are going to have one side a semiconductor, titanium dioxide, so that when we shine UV light, we can generate electron-hole pairs. And so on this side, the electron-hole pairs can participate in a reaction. And the other side, we have inert, no reaction. And these can be made very simply by, for instance, depositing a monolayer and then depositing the material that is needed to ensure that they're active. And this gives us these half-coated or Janus-like colloids. Here are some pictures that Drew Singh made, and he's also going to speak in the meeting. And you can see these colloids here have a nice little cap, and the cap is a catalytic site with titanium dioxide. And what we're going to do now is we're not interested now for this talk in the swimming, and you can also modify these colloids. You might not just have silicon dioxide, titanium dioxide. You can also use something like gold. Gold can be used to transfer the electrons into the titanium dioxide, which means you can also operate this not just with UV light, but also with visible light. So visible light enters, electron-hole pairs are generated on the titanium dioxide side. This causes a reaction, and then it will move. But we're not interested in this moving. We want to make a pump. So the idea is, can we take this structure? If it is moving through the fluid, if we fix it, if we glue it, if you like, to a surface, then the colloid itself, the structure isn't moving. The fluid will still flow. And the question is, can this be a unit for making a pump? Now, if we have an isolated structure, then we will have recirculating flows. The flows will mean that there will be either radial, distributed, or even a convex type flow system. That's not a pump on itself. So we need to turn this into a unidirectional pumping system. And the nice thing is, by using gold and titanium dioxide, we can use visible light, and we can of course also use UV light, which is still very effective, and we can drive this reaction by splitting water. So a normal water microfluidic cell can now be used to achieve flows. And here is where the shadow growth comes in, and this is the project by Ting Yu. You first take the substrate, that will be the bottom or the top of the microfluidic channel. This is just a substrate. Do some photolithography to make little posts, for instance. And now by shadow growth, you can decorate, for instance, one side here with gold. Then you can tilt it, and you can decorate the other side, for instance, with titanium dioxide. A little bit of silicon dioxide is added, and then there is a washing step to take away where the photopolymer is left, which then, taking this surface and turning it around, leaves us with these posts, which on one side are different than the other side. And so we can have titanium dioxide on one side and gold on the other side. And the nice thing is, of course, it's very fast. We can decorate the whole substrate very quickly, and we therefore have the whole surface decorated. And this now takes the swimmer, makes a post, and then we can make a post array. And a lot of these acting together, that's the idea, will cause a flow of fluid and could act as a pump. And that's what we wanted to test. And this is the setup. You can see lots and lots of these posts. They're about 1 micron by, or 2 microns by 2 microns. So very small compared to the typical microfluidic channel, which comes in at 50 or 100 microns. And now you have some light, then you have some reaction, and then you have walls that cause pumping, self-pumping walls. And the first control is whether the fluid flows, and it does flow. And you can also see that the flow increases with UV light intensity. So you get more flow because you have more reactions taking place, and that means more fluid flow. The next aspect that Ting Yu examined was what is the separation between these two posts. If the separation is very, very large, then we have very few posts and they will not generate any flow. But if we bring them closer together, then things start to pick up and we get a flow of a couple of micrometers per second, which is comparable to chemical pumps. And if they are too close together, then one chemical cloud on one side will overlap with that of the other side and then wash out and we are back to zero. So that also makes sense. And then using shadow growth, it's very nice and convenient to try lots of different geometries. We can try discs, we can try posts, or we can even try bars or something like this and see which ones work best. And we find that these little posts here, they work the best to generate a flow. And this is now some interesting physics, because normally at small length scales in fluid flow, we always deal with a no slip boundary condition, i.e. there is no flow at the surface. There's zero flow velocity here. And this means that if you are dealing with a pressure-driven flow, that you get this parabolic flow profile, the Posay flow here, which is also disadvantageous. You need an external pressure source, which we can get away with in this idea. And second is, often you don't want these flow profiles, for instance, in chromatography, because you might want to push things in an even way so that everything moves together. And this is now possible because now we're changing the boundary condition. We now no longer have a no-slip wall, but because we're generating flow here with our shadow-grown chemical pumps, if you like, we get a slip profile. And now you can do very unusual things. You can shape the flow profile in microfluidics now. For instance, if the bottom surface here is one where we get flow to the right, and the top surface is one where we get flow to the left, then we should get a flow profile which is linear and tilted. And indeed, that is what we observe. This is the bottom wall in our microfluidic, and this is the top surface, this is the ceiling, this is the floor, and here is the microfluidic channel, and we can see we go from a parabolic Posay flow profile to a linear one. And similarly, you can try other things. You can have one surface active or both active in the same way, then we get an inverted flow profile, or we have them opposing and we have the this engineered flow profile. So by tuning this, it gives a new possibility, and that is to make self-pumping walls, and they can be very easily generated because all of the steps are parallel fast steps, namely shadow growth, photolithography, and so this can be done on a large scale very, very quickly. And with this, I'm already at the end of a first example story, the chemical micropump that was enabled by shadow growth and oblique angle deposition. And now I would like to turn to a outstanding question in spectroscopy that was enabled by glancing angle deposition. And this is the observation of a single chiral or single nanostructure in spectroscopy and determine its handedness. So very briefly, chirality is handedness. Corkscrews can be left-handed or right-handed, and so can pasta can be left-handed and right-handed, and many things in nature are left and right-handed. The definition comes from Lord Kelvin, and it basically means that if something is different from its mirror image, like the left hand and the right hand, then they're chiral. And if they're the same, they are achiral. So this chair is identical to its mirror image. And the physics operator would be parity. And if we have parity, then this is the symmetry operator that can distinguish between chiral objects and achiral objects. And the importance, of course, is that many molecules that have biological significance, sugars, amino acids, tend to be chiral. And here is a picture of a DNA molecule, and it's also chiral, it's twisted. It actually does have a corkscrew shape. And we need to observe them, and the typical way to observe them is using circularly polarized light. And here is a schematic on how this would work. If the circularity of the light fits the sense of this helix, the helicity, then you might have a strong interaction, higher refractive index, more absorption. If the handedness of the light, left or right circularly polarized, does not fit with the circularity or handedness of the molecule, you have a weaker interaction, lower refractive index, less absorption. But this is only a schematic, and it's not a good one, because typically the molecule is, of course, much, much smaller than the wavelength of light. So the interaction is really a very, very weak one. So these are very weak optical effects. But here to the rescue can come chiral nanohelices, and they can be grown by a method that we at some point termed nanograd. So we use block copolymer micellar lithography to generate a surface with nanoparticles, in this particular case gold nanoparticles, which then serve as a growth point for shadow growth and to make 3D films. And this allows us to make some really exceptionally small chiral structures. And of course, this is one of the strong points of GLAD. We can make these right-handed or left-handed helices depending on the rotation sense of the substrate. And this was implemented by John Gibbs and realized by John Gibbs and Andrew Mark. And John Gibbs is also going to give a talk in this meeting. And here you can, for instance, see metallic nanohelices made out of gold, silver, copper, and other interesting materials that are only 19 nanometers tall. And just to bring home how small these structures are that GLAD can make, here is a gold helix that it was made with a polymer first, and then the polymer was turned into gold. It's a well-known paper in metamaterials for the infrared, and it was used using 2-photon lithography. Now, in 2-photon lithography, you have a voxel or a write pixel for writing, which is about 100 to 120 nanometers in size. But GLAD is, of course, able to do this much more easily. So in 1 pixel that you can write with 2-photon lithography, with GLAD you can make much, much smaller structures here, like this multi-turn helix. And the beauty now is that we can make them small enough to minimize scattering effects, but large enough to be much, much bigger than a molecule. And moreover, we can make them from, for instance, plasmonic metals, so that we have a large conductor, basically a very strong antenna that can interact with light. And in this case, it's a spatial, a shape chirality, because we are having this helical shape. And this then means it has an enormous polarizability, and in particular, it also gives rise to optical activity, i.e. it will interact with left and right circularly polarized light. Now you can take a wafer and you can sonicate it, and you can put these helices in solution. Then you have many billions of them, and you can watch them with left and right circularly polarized light and look at the difference between the absorption of left and right circularly polarized light. That's what's done in chiroptical spectroscopy, and you get very, very strong signals, 100 to 1,000-fold stronger than what you do with molecules. So just for the experts here, these are something like 2,500 millidegrees of ellipticity in a picomolar solution. So it's really, really strong. And with this, we wanted to address the following question, which is of interest in plasmonics. But first, let me remind you that, of course, in typical chiroptical spectroscopy, i.e., let's say you have a sugar solution or something, and you want to know, are there chiral molecules in there? You make a solution and you send in left and right circularly polarized light, and then you see a difference in the absorption. And if you see a difference in absorption between left and right circularly polarized light, and you have all of these many molecules in this solution, then it's a absolutely clear, unequivocal signature of chirality. Then you know your solution is handed, right? And it works because you've got lots and lots of them that are all isotropically distributed or oriented. And in plasmonic spectroscopy and in nanospectroscopy, it's of course nice to be able to watch just one single structure. And this now gives us a problem. And in fact, I think it's a major problem, in particular for chiral spectroscopy. And the problem is that by looking at a single structure, if we hold it, if we clamp it, if we put it on a surface, if we grow a film on a surface, I believe most of the results that are reported have got nothing to do with true chirality, because you can get differences in the absorption of left and right circularly polarized light very easily, even with things that are not chiral. And I want to demonstrate that to you with a water molecule. So a water molecule here, you can also imagine it could be a plasmonic antenna that has this V shape. This is not chiral because it has a mirror plane of symmetry. But if we put it on a surface, it can become chiral. Now, this person is pointing a finger at you, and the idea is there is light coming in this direction. Now, let's imagine we have these structures and they are fixed on a surface. So they're not moving, they're fixed. And we can see, depending on how we take this achiral water molecule, how we orient it, that there will be a favorable interaction with one circularity of the light, and the opposite circularity in this case will show less interaction. And opposite is the case here. That means if we had one of these experiments and we, for instance, had the surface with lots of them all anchored on the surface, if we send circularly polarized light, we will see a difference between left and right circularly polarized light. And then we could think it's got something to do with chirality. Yes, it has, but it's the chirality of the experiment of orienting this object. It's not the chirality of the actual scatterer or object we're looking at, because we know it isn't chiral. This is an achiral object, right? And so a lot of the experiments that are done on surfaces with chirality are wrong. And in particular, this one here, it's trying to say that you can probe the chirality of a single molecule, and these molecules are embedded in a polymer film, and it makes the same mistake. It's got nothing to do with chirality. It sees large spectral differences because there are birefringence, linear birefringence effect. So how can we get around this, and what really is the problem? Well, the problem is again summarized very nicely by Wolfgang Pauli, and he said that God made the bulk and the surface was invented by the devil. And that is because there are many effects at the surface, and in our case it means any surface here up is different from down. Otherwise there wouldn't be an interface here, right, between two different media. So we already break symmetry at the surface because up is different from down. So regardless of what you put there, you've broken symmetry. And that means objects that you place there will appear or can appear chiral in their experimental arrangement, and it will never be a measure of the objects, the molecules, the plasmonic structures chirality. And you can get huge effects because of this symmetry breaking at the interface, this parity, which has got nothing to do with the objects you make. But we still wanted to find a measure to detect the chirality in a single nanostructure or nanoparticle. So how do we get around it? If we fix it, then we have a problem. Because if we fix this structure, then we are liable to measuring the wrong thing. So how can we solve it? Well, this is the solution to this problem that we pursued. If we let this structure tumble freely in solution, then we can use the ergodic principle and we can do a true error-free measurement of chirality with a single nanostructure. Because one nanostructure that's tumbling in solution will explore all the orientations, and that then means that we can, over time, we can use the time average to get the ensemble average, which is what the ergodic principle tells us. So here is how to measure chirality in a single nanostructure to avoid all the artifacts you get on a surface. And this is the PhD work of Johannes Sachs. We have a single nanostructure in solution, and we illuminate it, we collect the light from it. This will be tumbling because of Brownian motion. It will be moving by itself in solution. And then we take the light, we split the two polarizations, left and right CP, and we simultaneously observe them on a detector, on a CCD detector, and then we can take the difference in one shot. We can then take the difference and we know what the intensity difference is. And the slow diffusion in solution is ensured. If we make the solution a little bit viscous, then this will not translate away. But the beauty is the rotation goes with 1 over r cubed. So it goes very, very fast, where the translation is linear in r. And so we will have a lot more rotation and translation. So we can watch it long enough. It's not translating away, but we can be sure it's tumbling around and sampling all orientations. And now the idea is the following. The particle will move because of rotational Brownian motion. In particular, it will rotate. And as we take this movie here, we will have snapshots of different orientations. And at each orientation, we can take a spectrum. So we will get a movie, a time series of spectra, each one for another orientation. And then we can take the time average, i.e. we average the time series of spectra, and this must be equivalent to the ensemble spectrum. That is what the ergodic principle says. And the ensemble spectrum is the average over all orientations. And thereby we have eliminated the possibility of the artifact that you would get in lots of experiments on surfaces. So let's do some experiments. The first experiment Johannes, of course, did is to take a sphere. Regardless of how you orient the sphere, it's always achiral, right? And here are frames at a particular wavelength, and we see that the intensity difference between left and right is 0. And that's not surprising, because the sphere, however you orient it, will never show an intensity difference. And if we take the average, the time average of all of these frames, we get a 0. That is what we expect. That we don't expect anything chiral here. Let's take a rod, a nano rod. Now it already gets interesting, because now we see fluctuations. That means there is momentarily a difference between left and right in the intensity. And if we were to plot these spectra, all of these points here in the time series, we get lots of spectra, and we could be fooled and say, oh, we've taken a spectrum. Here's a spectrum. That's the wavelength. We see an intensity difference between left and right. We say, oh, we've got a chiral probe. Well, of course, it's wrong, because the time average here of all of them added together again gives 0 intensity difference, like it should. This is compared to ensemble averages. There is no chirality if you have a solution of rods. But note that there can be fluctuations. And so if we were to use it in a fixed geometry, we would have one fixed geometry. We could be fooled into thinking there's something to do with chirality. And then finally, now the real sample, if you like, that we're interested in, let's take the helix grown with GLAD. Let's again take the movie of orientations, and we again see fluctuations. So one single snapshot is not going to tell us the answer. We need to take enough snapshots to sample all orientations, and then we can take the average, and the average you can already see here has a deviation from the 0 line, so there is an intensity difference. And in fact, for the left-handed helix, it's this blue line. It comes out very, very clearly. and we can repeat it with another helix and we get the same result as a comparison. This is the sphere here, 0 result. And then of course with GLAD we can grow the right-handed helix and we get the opposite signature. So this is a really true measure of chirality, and it's for one single nanoparticle. And how is it possible? By sampling all possible orientation, which we do because the particle itself experiences Brownian motion. And we can, of course, do some control experiments. We can take lots of these helices and put them in solution and make sure that the spectra correspond to what we see here. And the idea is that the time average is the same as the ensemble average due to the ergodic principle. However, there is one slight and very interesting difference. By doing this experiment, we measure something you could never measure here on the ensemble average, because any ensemble of nanoparticles is never made of identical particles. There are always slight variations in the fabrication. So this is a measure of many particles which all are a little bit different, whereas by taking the time average of a single particle, you get the actual true chiral observable because you are just watching one, and so you avoid all the fabrication differences in these samples. And this is the idea now. The time average of one single structure gives us here an ensemble. In this particular case, it's really an orientation average of the identical copies if we'd had lots of them. And this is a true measure of chirality, and we can be absolutely sure that we believe this. And here's a control. We can also use GLAD and add a little bit of magnetic material, and then we can use coils, and we can then deliberately orient our helix, and we can do it in such a way that we map out all spatial orientations. So we are mimicking the isotropic orientation distribution. And here is the experiment, one of many, and we show that the magnetically oriented one follows very closely or exactly this Brownian one, i.e. the random orientation really is sampling these different orientations. And so this is a measure of chirality, and I will just have a few minutes at the end and then I'm done. So the first one was oblique angular deposition to make a chemical pump, GLAD to make these strongly scattering nanostructures, and we can thereby solve this problem on how do you really measure chirality with nanostructures, and in particular single ones. And now finally, I'd like to talk about, in my opinion, a very promising material possibility that is also afforded and can be combined with GLAD growth. And so here we are inspired since a long time. This is work going back together with Ambrish Ghosh, who is also going to give a talk at this meeting, that we wanted to mimic this motion of a bacterium, so the helical motion. And we've been looking whether we can make artificial structures and move them through interesting biological media and to penetrate different barriers. And we were successful to go through mucus, we've gone through the eye, but this is not what I'm going to talk about. I just want to say why we're doing this with these GLAD structures, because a lot of these tissues, most tissues, have a microstructure, i.e. they are porous to some extent, so you can move through them more easily if you're small enough and you fit through the cavities in these porous structures, in these macromolecular porous structures. And the opening is several hundred nanometers, and that fits very beautifully with GLAD. So you can take a structure, sonicate it, have a bit of a magnetic material here, use a rotating magnetic field, and the structure will then be able to propel. And the idea is it can go through these macromolecular networks, and we can use them to penetrate tissues. But one interesting question that arises is, what about the magnetic material? And we can, of course, use iron, nickel, cobalt, iron oxides, but the strongest magnetic material, neodymium iron boron, we cannot use because we cannot fabricate it with vapor deposition. And here, and I'm almost done, is a very interesting material, and it's quite curious. If you add platinum, which is not magnetic, to iron, then their interaction will cause a super strong magnetic material. It's almost as strong as neodymium iron boron, almost the same. It's really exceptionally strong. Plus, these are all biocompatible materials. They're not corroding. They are shown in many studies to be non-cytotoxic, and they have this incredibly high permanent magnetic moment once you magnetize them, this high remanence. And really tenfold of what you can do with the materials that you normally deposit. So this is a wonderful material system, and Vincent Kadiri in his PhD has demonstrated this. You can incorporate it by co-depositing iron and platinum, and then you will be not yet in this phase that you need, which is the L10 phase. You can see this sort of layered between iron and platinum here, but you get this very easily after co-deposition by annealing. So after annealing these structures, then we have nanopropellers with an annealed magnetic moment, strongest possible magnetic moment, fully biocompatible, and then you can add things to, for instance, enable the transport into the cell or bring genetic materials, as was demonstrated in these studies, including toxicity studies. But there have been many in the literature, so this material is really very, very promising. And I'm going to end with this. You can see these are sort of curves for iron, the green and the red, and the black one here is iron platinum. It's a hard magnet, and it's very, very promising because it's almost as strong as neodymium iron boron, but has the advantage that you can use it in vapor deposition, in GLAD, in oblique deposition, and it doesn't corrode and it isn't toxic. And with this, I'm at the end. Sorry that I failed to share my screen right at the beginning, but I hope you could follow the rest of the talk. And I want to thank everyone and also the organizers for the meeting and you for your attention. Thank you.
Thank you, Professor Fischer, for this wonderful talk on active nanostructures and chiral spectroscopy. So now I would like to request all of you, if you are willing to ask any question, first raise your hand. So you can raise your hand just clicking on the option in front of your name in the list of participants. So I will allow one by one to ask question to the speaker. Zifeng, yes, you can ask question.
Yep. So thank you, and thank you, Professor Fischer. And I'm the Zifeng from Hong Kong Baptist University.
Hello.
Hello, hi.
Hi.
Long time no see.
Yes.
Very fantastic work. And I have a question about this chiral and the CD of this single nanohelices. And your work is very fantastic. And I have two questions. The first question is about technical questions. So how you can guarantee that you can trap that for a given nanohelical as a function of time, rather than where you have chance to monitor the different particles.
So how can we ensure it's long enough in the microscope focus for the measurement? Is that the question?
My question is how you can guarantee that you watching at the same particle as a function of time.
Yeah, because we also have another channel in the microscope. So we take the light scattered on a CCD camera and we see in dark field illumination a bright spot. So we can see where the spot is and we can be sure it's only one, and we can be sure it's there for our observation. In fact, we want to make sure it's more or less in the center so that the light then, if you map it onto the spectrometer, hits the slits more or less in the center. And so you can actually see it. You can see it on a normal video camera. That's the beauty with dark field microscopy. It's very bright. You can see one single nanostructure very easily.
So you will reduce the concentration of your colloidal.
Yes, yes, of course, very, very low concentration, so that you only have one at a time, and making sure the solution is a little bit viscous so it doesn't drift away.
Mm-hmm. And another related question is about that. So just like you publish in the Nature Materials, you measure the CD of these assembled nanoparticles. And of course, you can also monitor the CD of the array, which going to be fixed on the surface. And you can eliminate the median dichroism by you rotate the measurement angle. And so
Not fully, only if it's uniaxial. If it's not uniaxial, then you cannot eliminate it by rotation. So you can only make this if it is uniaxial, then it's correct. But if it isn't, if it has two axes, if it's a biaxial system, then rotation alone does not eliminate linear dichroism or birefringence.
Okay. So use your technology, is it possible you can study the interaction between the particles, the particle to particles plasmonics interaction, and how this interaction can affect the CD? Is it possible?
I'm very sorry, I very briefly blanked out. So I just heard plasmonic interaction. So what did you?
Oh, yeah. So my question is, you can can you study how this particle and the particle and the plasmonics interaction between them, how this can affect the CD of the particles?
Because we can, if we, for instance, make it magnetic, we can actually deliver a particular orientation. So we can take every orientation and we can watch the spectrum accordingly. So we know how each spectrum corresponds to the orientation of the particle. And so we can see that. And I mean, if the question was about two particles interacting with each other, then I don't know how to do that, because that would mean you would have to have them dancing around each other, which I don't quite know how one would control that.
Is it you luck? You have luck enough that you tracked the two particles.
We never tracked two. We only looked at one single one. Yeah.
Yeah.
Only one single one to have single particle spectroscopy.
I see. Okay. Thank you.
Yeah,
Very
thank
nice
you.
work. Very nice work.
Thank
Nice
you.
to see you again.
Yeah, very good to see everyone via WebEx.
I request Professor Neeraj Khare to ask question.
Hello, Professor Fischer.
Hello.
Yeah, hello. I'm Neeraj Khare from IIT Delhi. It's a very, very good talk. I really enjoyed the whole talk very much. So very good. My question is more related with the first part of your talk. You have used the titanium dioxide and this gold, and then it becomes kind of visible light active. So it's because of the plasmonic effect you are getting this thing.
Yeah, so this is known. This is what people have studied a lot. Titanium dioxide is a really much studied system. And if you add metals, it somehow brings these Fermi levels a little bit closer. And one believes that there is hot electron injection. So you basically have this antenna effect and absorption of light, and then it can inject more effectively in titanium dioxide. And then you can use visible light, also green light, to excite these structures.
Okay, so have you tried this kind of thing in any other materials for this kind of application?
Have we tried it in where? I didn't hear that. I'm sorry.
The other materials apart from TiO2 and this gold?
No, we mainly use TiO2 because we want this as a control to be able to switch it on and off with light. But you could use other materials, of course, ones that are always catalytic, then it will always pump. And you can make other material combinations, also other semiconductors. It's really more or less the principle, and it's not just this material where this will work.
Okay. Okay, thank you.
Thank you.
Thank you.
So now I request Professor Ambrish Ghosh to ask question. Yes, Professor Ghosh.
Yes. Yeah. Hi, Pierre. Very nice talk. Really enjoyed it. I had a
Hello, hello.
question. I had a question about the isotropic averaging of the single nanostructure that you just mentioned. So the helix would have different rotational diffusion times depending on whether it's rotating about the long or the short axis. Now it's probably a small effect, but is it really fair to say that you are doing a uniform averaging if you allow it to tumble due to Brownian motion? That's my question.
Yeah, I hope it is, because the rotation about the short axis is so fast that we don't resolve it. And the rotation that we're really after, so if I take my pen and I were to rotate it about its axis, this is happening very fastly. And the one that we're really following is the one in space. And so I think we are really sampling all possible orientations in this system. For any one given orientation, it will already be averaging across this axis fast, and then in addition, it will also move in space. So I hope, and at least according to calculations and measurements, it does seem to correspond to what we would expect.
Well, so if I were to do an average over theta and phi, I think you're basically doing an integral of cos theta d phi. But right, but what you are assuming when in the sort of out here is that both the theta and the phi velocities are the same, and that's my doubt really, whether that's correct or
But
not.
I think one is faster than the other. So for any one recording of one theta, if that's your orientation in space, one orientation, we will have already multiple positions around its own axis averaged. So it's, if you like, a double average happening at two different times. We cannot resolve the orientation along here, whether it's rotating, that's too fast, but we can see this.
Okay, so it is implicitly assuming that there is a large separation of timescales that has to be assumed.
That one is significantly faster than the other, and in order to collect enough light, we need to hold this a little bit. So, or at least make the solution viscous enough that it keeps each position. So a measurement takes something like 20 seconds or so. Not one orientation, but the whole measurement.
Right.
And in this time, we can be sure it has spun quite efficiently about its axis.
Got it. Okay. I had another small question. This is related with the titanium dioxide and the UV light. So how long will this pump work? I mean, will it continue working forever?
Yes,
as long
I guess so.
Right? Yeah. Okay.
Yes, that's the beauty in these systems. As long as, same with the ones that use a catalyst and a fuel, as long as you provide fuel, it will keep going.
And is there anything special about this titanium dioxide? Like what phase would it have to be?
Yeah, so there is between anatase and rutile, there are some more effective ones. So after annealing, you end up with anatase, and it tends to be more effective in the catalytic process. But if people want to work with this, you can even buy particles that are synthesized. So you can have even titanium dioxide particles you can buy. And after deposition and just a very simple annealing process, we can ensure that they all are fairly active. So it's not a difficult step.
Okay, great.
Thank you. Thanks.
So now I request Professor Yiping Zhao from UGA to ask question.
Here, excellent talk. So I still have some question regarding your second part. So can you use the system to measure the optical rotation of a single particle?
No, I don't believe so, because it's so weak, right? I mean, the thing that we rely on is that we actually have some extinction and the rotation of a single one. I don't think it's measurable. It's a very, very weak effect. Yeah.
Okay. Another question is that, so even after your average different orientation, should the like a linear dichroism still play a role, because the particle themselves it's not isotropic, right?
Yeah, so there are no.
Oh,
I
yeah,
mean, we average out linear dichroism, and any effect that are linear birefringent like linear dichroism are gone after this average, after all orientation average. And it actually is even a little more complicated, because if you think about it, then even a rod should not show an intensity difference between left and right circularly polarized light. And this has to do with the condenser and the light cone, and so it's even the optical system introduces some problems typically. And but the beauty is, if you take this average, if anything that survives, you can be sure it's chiral, and this is what we're taking advantage of here.
Sure. Thank you.
Thank you. Thank you very much.
Okay, thank you, Professor. If there is no any more question, I would like to ask last question. So, as you are measuring the chiral measurements in the liquid phase, so can we also do it on the solid phase, like the sample grown on the glass or quartz substrates?
Well, that's the difficulty, right? If you do it on a substrate, then you
Yes.
have a fixed orientation, and then you need to be extremely careful, because any effect that is due to orientation or birefringence, as it's called, will be orders and orders of magnitude bigger than what you're looking for. So it's rather tricky. Some people do it by spinning, but then you need to assume that it's uniaxial, or by spinning and flipping. But these are all approximations to some extent, because also your geometry in your experiment is not truly sampling all possible orientations. So the answer is, it's possible. If you know the system very well, then you can kind of calculate it out or be very careful. And otherwise, it's actually tricky. It's not entirely clear whether this is really going to be a true measure of chirality. And if your system is not uniaxial, if it's biaxial, then no matter of you twisting, rotating your sample, you'll never get rid of these artifacts. And that can be the case in a lot of thin film systems.
Okay. Okay.
So
Thank you, Professor.
as Wolfgang Pauli said, the surface is the devil. So the surface is
Yes.
tricky.
Yes, it's true.
Okay, thank you very
I
much.
think, yeah. Okay. Thank you so much for this wonderful talk, so Fischer. So now I would like to start the next session. So it will be started actually at 11:30 a.m. So we have 10 minutes. So we will be starting just after 5 minutes. You can have a 5-minute break. So now we are back. So we are going to start the session. And I would like to request Professor Prashant Mishra to chair this session. So Professor Prashant Mishra is a professor in the Department of Bioengineering at IIT Delhi, and he is the ex head of department and ex associate dean students at IIT Delhi. He is a core committee member of nanoscale research facility in IIT Delhi. His research area is protein engineering, non-aqueous enzymology, nanoparticles-based drug delivery, protein-based nano devices, and nano biosensors. So I would like to request Professor Mishra to chair this session. Over to you, sir.
Yeah. Very good morning to all of you. And first of all, let me thank the organizer for inviting me for this conference. I'm really glad to be part of this GLAD meeting. And we are going to have the first session of lectures, which is going to have 3 distinguished speakers who are going to talk about the thin films by different methods. And to start with, we have first speaker, Professor Motofumi Suzuki. Dr. Shashank, can you share his CV?
Yes, I already shared.
Okay. Somehow it is not coming in my system.
I have already shared. Anyone else can see?
Okay, let me just look at my system.
Okay.
Yeah, so Professor Motofumi Suzuki, he received his PhD in 1998 from Department of Engineering, Kyoto University. He has worked as a researcher in Toyota Central R&D Lab, Japan, from 1988 to 2002. Then he held positions of associate professor at Department of Microengineering, Kyoto University, Japan, from 2013 till present. He is working as a professor at Department of Microengineering, Kyoto University, Japan. His current research interests include the optical property of nanostructured thin films and synthesis of novel nanostructures. He is a member of Education and Research Council, Vice Dean of Graduate School of Engineering and Director of Kasturba International Technology Center. He is a member of the Japan Society of Applied Physics, the Japan Society of Vacuum and Surface Science, the Japan Society of Mechanical Engineering, SPIE, ABS, and ECS. He is going to deliver a talk on light trapping sculptured thin film. I would request Professor Motofumi Suzuki to address the gathering. Thank you.
Okay, thank you for kind introduction. Okay, so thank you, Professor for kind introduction. First of all, I would like to express my sincere thanks to organizers of this symposium for giving me this opportunity to present our recent topics. It's my great honor to be here. Okay, today I'm going to talk about the light trapping sculptured thin films. So in this presentation, first I very briefly introduce you the sculptured film films. Then I'll discuss the light trapping structures. After that, I'm going to introduce some examples of the light trapping sculptured film films. They include the gold nanorays for the spheres, thermoplasmonics, the Y-grid polarizers, and after that, I'm going to present our recent topics on the improvement of photocatalytic efficiency by light trapping structures. Okay, so now let me briefly introduce the sculptured film films. As you know, the sculptured film films are kind of the physical vapor deposition film films. And typically, they are deposited in the high vacuum evaporation system. Here, the deposition system is equipped with a special substrate holder, which has a rotation system around the two axes. During the conventional physical vapor deposition, vapor is deposited on the substrate from a normal direction in the vacuum so that the flattened uniform thin films are produced. But on the contrary, during the oblique angle deposition, the substrate is set obliquely and sometimes rotated in plane, as indicated here. If the substrate temperature is sufficiently low, unique.
Excuse me, Professor Suzuki, can you please make it large, full screen?
Okay.
Okay. Yeah, thank you.
Is it okay? Is this okay? How about?
Yes, it is okay.
Okay.
No, okay.
Okay. So unique nanocolumnar structures are created by oblique angle deposition technique. And these obliquely deposited film films show the various useful properties. It is well known that they show the optical, magnetic, and mechanical anisotropies. And they are already commercialized. For example, the most successful example was the videotape and the metal polarizers, which are produced by the so-called Fulcan process, were available at least 10 years ago. And the thin film wave plates, which have huge birefringence, available from a Japanese coating company. And in addition to these physical anisotropies, the obliquely deposited thin films show the large surface area, and they have the huge porosity and some other useful properties. More than 20 years ago, Rakutaki et al. Have proposed the concept of the integrated sculptured thin films with multi-layered structures. In the integrated sculptured thin films, both the functional materials and the functional shapes can be multi-layered. In fact, we demonstrated already that the nanocolumnar structures with various morphologies are integrated only by oblique angle deposition technique. So it is expected that multi-layered obliquely deposited thin film have the great potential to realize the innovative functions and the multifunctional nanosystems. Therefore, the sculptured thin films are the most possible candidate for the light trapping functional thin films. Recently, various types of the light trapping structures are investigated for the application to the sensors, thermal emitters, and thermoplasmonics. For example, this is the typical layered structure of our local plasma resonators, which is composed of the silver mirror, dielectric spacer, and nanostructured metal absorbers. In the field of the metal materials, many people focuses their attention on the so-called perfect absorbers. The typical perfect absorbers also have the mirror, dielectric spacer, and the nanostructured metal patterns. So this is the structure of the typical waveguide mode sensors. they are very similar to the local plasma resonance sensors, but they are composed of the analyte, dielectric waveguide layer, absorption shown layer, as shown here. So because the interface of the analyte and the waveguide layer is the perfect mirror due to the total internal reflection, the waveguide mode sensors have also the structure of mirror, dielectric layer, and absorptive layer. Therefore, you can recognize that these absorbers have the optically common structures. Okay. So in order to trap the light in the functional absorption layers, the high reflective mirror is necessary, and also the tuning optical constant thicknesses of absorptive and dielectric layers are required. So it is easy to meet this demand if we use the oblique angle deposition technique. So now I'm going to show how to tune the optical properties of each layer and how to find the optimum structure efficiently by using the oblique angle deposition technique. And I choose the gold nanorods arrays for surface enhanced gamma scattering for the example. We have successfully prepared gold nanorod arrays on the SiO2 template layer nanostructured by the oblique angle deposition technique. SiO2 was deposited along these two blue arrows so that the SiO2 layer becomes porous and showed an isotropic surface morphology. On this isotropic SiO2 layer, the small amount of the gold was deposited from the oblique direction so that the elongated nanoparticles, so-called nanorods, are assembled on the SiO2 template layer. The gold nanorod arrays show the excellent surge performance, and they have already been commercialized from the Japanese coating company. But the laser light for surge measurement are not well confined to the gold nanorods. Therefore, further enhancement of the surge is expected by improvement of the coupling of the local plasma with photon. The strategy to improve to trapping the light into the gold nanorods array is to recycle the light scattered by the gold nanorods arrays by using the multi-layered structure shown here. In this multi-layer, gold nanorods and SiO2 layer named shape control layers are the same as those I showed in the previous slide. The key points are the mirror and the layer of SiO2 named phase control layer. The role of the mirror is to reflect the light transmitted through the nanorods, of course. And the role of the phase control layer is to tune the optical path length. But we aim to minimize the reflectance for the better coupling of the local plasma with the photons. So in order to find the optimum structure quickly, combinatorially multi-layered structures are fabricated. In this combinatorial structure, we changed the thickness of the gold nanorods and the thickness of the phase control layer over the sample step like this. This is a photo of the resulting samples. The thickness of the phase control layers increases from left to right. And the thickness of the gold increases from bottom to top. So you can see clearly the checkerboard-like patterns in the vivid colors due to the interference. SEM images also indicate that the much-layered structures have been successfully prepared. Okay, and these three spectra are typical reflectance spectra measured on the different parts of the samples. when the thickness of the gold is 5 nanometer or 10 nanometer, reflectance changes significantly, and there are some perfect absorption conditions. Under these perfect absorption conditions, the incident light is well trapped in the gold nanode array. So now I'm going to introduce the example of the applications of this kind of the light trapping structures. The first example is the first surface enhanced Raman scattering. This figure shows the surface enhanced Raman scattering spectra as a function of the thickness of the phase control layer, SiO2 layer. Okay, horizontal axis is the Raman shift, and the vertical axis is the thickness of the SiO2 layer, and the Raman scattering intensity expressed in the colors shown here. The first intensity becomes very strong when the thickness of the phase control layer is 130 to 170 nanometers. Comparing with the reflectance spectra shown here, it is found that the first is strong when the incident light is well trapped in the gold nanodes. The third intensity measured on the light trapping structure is about 50 times higher than that measured on the gold nanode arrays without mirror. So, as I mentioned before, the gold nanode arrays without mirror show the 10 to 7 times enhanced Raman scattering. So that the enhancement of the enhancement factor of the perfect absorber may reach to the 10 to 8 or even higher. This number is quite good for the further application. Let's take a close look. Take a look at the measurement results of the further and absorption. These are the comparison of the Raman spectra and the absorption spectra as a function of the wavelengths for the samples with the SiO2 layer with different thicknesses. When the, so now the dotted line indicates the Raman excitation laser wavelengths. So when the absorption at the Raman excitation layer laser wavelength is low, their source becomes quite weak. On the other hand, when the absorption at the Raman scattering wavelength region is low, Raman scattering is also, Raman scattering intensity is also not strong. So in order to obtain the strong surface enhanced Raman scattering, it is necessary to enhance the both to increase the absorption for both the excitation laser light and the Raman scattering light here. So these results provide us with the sufficient evidence for the twofold surface enhancement mechanism. These multi-layered structures, thin films are expected to apply to sensing biomarkers. So, however, it is difficult to extract biomarkers directly from the human skins using the thick, solid substrate. To overcome this problem, we propose a multi-layer thin film flake dispersion gel. The multi-layer thin film was prepared on a mica substrate, and the multi-layer small pieces are mixed with the HEC gel by a mixer. The mixing process was optimized to obtain the flakes of about the size of the 10 micrometers, so that the optical properties of the multi-layer film can be preserved. The first characteristics of the flakes dispersion gel were tested using the 4,4' biprigine BPY solution. The BPI molecules diffused through the highly porous gel within the seconds, producing the significant surfing signals. So these active flakes dispersion gel can be used directly on the skin surface to collect the body fluids from the sweat for biomarker sensing. On the second topic is the thermoplasmics. The trapped light in the gold nanoparticles are converted to the thermal energy, and such thermal energy can be used to drive the microfluids. So imagine gold nanoparticles in the water and irradiating them with laser, we can create the microbubble easily. Heating the water gas interface by using the localized thermoplasmic heat, various types of the flows can be generated as indicated here. For vortex flow, particle focusing flow, particle sorting flow, and strong mixing is also possible. By integrating these emerging thermoplasmic microfluidics technologies with sensing technologies, I hope that Radon nano gold will be really realized in the near future. And another topic is the low reflectivity wire-grid polarizers. The similar light trapping structure can be created on the wire-grid polarizers to reduce the fluorescence to the reflectance, to reduce the reflectance of the wire-grid polarizers for the application to the liquid crystalline projectors. At first, the conventional aluminum wire-grid polarizers were fabricated, and the layer of FiO2 was deposited by ordinary sputtering. Then the FeFi2 as an absorber was deposited by ion beam sputtering at the glancing angle deposition at the deposition angle of 87 degrees. Because of the shadowing effect, sputtered FeFi2 adheres only to the top of the wire grids covered with FiO2. As a result, typical perfect absorber structure, aluminum mirror, FiO2 spacer, and thin ion diaphilified nanoparticle layer has been successfully fabricated. The reflectance of the TE polarization is reduced down to the less than 1% because the TE polarized light is absorbed by the FeFi2 nanoparticles. For the low reflectivity wire-grid polarizers with high thermal and photo durabilities are now used in the liquid crystalline projectors. So, finally, I'm going to introduce our recent topics on the improvement of the photocatalytic efficiency by using the light trapping structure. As you may know well, photocatalyst is used for the various applications. Many researchers are developing the photocatalytic materials, and there are also many reports on the nanostructured photocatalytic thin films. Basically, for the stain resistance and water splitting, solar light is used. On the other hand, artificial light such as black light is used for the air purifiers and water purifiers. But recently, UV LED are developed, and they are desirable more than black light from the viewpoint of the energy efficiency. As indicated in this figure, the spectrum of the LED is much narrower than that of the solar spectrum and that of the black light. So for the application using LED, light trapping structure may be useful. So we tried to clarify the effect of the light trapping structure on the photocatalytic performance. So in the light trapping photocatalyst, the absorption layer is obliquely deposited TiO2. We have reported the photocatalysis of the single layered obliquely deposited TiO2 thin films with these morphologies. The photocatalytic activity of the sculptured TiO2 thin films are much higher than that of the uniform TiO2 thin films, and it shows maximum at the deposition angle of 70 degrees. This figure indicates the photocatalytic efficiency of TiO2 columnar thin films as a function of the thickness. The photocatalytic efficiency increases with increasing the thickness and saturate at the large thickness. If the photocatalytic efficiency at depth x is proportional to the intensity of the UV light at depth x, the efficiency may be written in this equation. The model function fit with the experimental results, and from the value of the fitting parameter alpha, we can conclude that the interior surface down to 200 nanometer works as the photocatalyst. So we tried to improve the photocatalytic efficiency of this region by light trapping structure. First, we designed the structures using the model calculation. The model of the light trapping structure is shown here. The mirror is aluminum, and the absorption layer of TiO2 columnar layer, of which thickness was fixed at 200 nanometer. And we changed the thickness of the SiO2 layer sandwiched between aluminum and the TiO2. The red region corresponds to the high absorption where the incident light is trapped to the TiO2 columnar thin films. Absorbance changes periodically as a function of the thickness of the SiO2. So we found that UV light around the 340 nanometer can be confined to the TiO2 layer due to interference. So we tried to make the designed layered structure by oblique angle deposition technique. First, we deposit the aluminum and SiO2 from the surface normal, but here we changed the thickness of SiO2 from 130 to 210 nanometers. Next, we deposit the Ti2O3 under the oxygen atmosphere at the deposition angle of 70 degrees.